Good day, Doc. Good day, classmates. This is the continuation of the Unit 5, which is the Quality in Production and Operations Management. So I will be discuss the part 2, which is the Accepting Sampling. Chapter Objectives. Understand the operation of acceptance sampling. Draw an operating characteristic for single, double, and multiple sampling plans. Select appropriate plans to meet particular conditions, and understand the OC curve and AOQ. The acceptance sampling. It is another category of statistical quality control that inspects products after they are produced and not during the production process. It involves selecting a sample from the entire batch of products and deciding whether to accept or reject the whole batch depending on the quality of the sample. It also involves inspection before the process, in which raw materials are tested before they are used in the production process. So acceptance sampling is used when an organization has a large product line and it is not possible to the inspector to check every item from the batch. However, it requires huge cost and efforts of an organization and has a scope of errors. Sampling is more economical than 100% inspection. The quality of the sample is used to judge the quality of all items in the lot. Although both attributes and variables can be inspected by acceptance sampling, attribute inspection is more commonly used, as illustrated in the picture. This is a flour bakery in the Villarica, Georgia, that uses a digital camera to inspect just baked sandwich buns as they move along the production line. Items that don't measure up in terms of color, shape, seed distribution, or size are identified and removed automatically from the conveyor. Acceptance sampling can be applied either when materials arrive at a plant or at final inspection, but it is usually used to controlling incoming lots of purchased products. A lot of items rejected based on an unacceptable level of defects found in the sample can be returned to suppliers or be 100% inspected to cut out all defects, with the cost of this screening usually billed to the supplier. However, acceptance sampling is not a substitute for adequate process controls. In fact, the current approach is to build statistical quality controls at suppliers so that acceptance sampling can be eliminated. When to use acceptance sampling? Acceptance sampling can be used in many different ways, including determining whether or not a batch of products should be manufactured, testing the effectiveness of new manufacturing processes and equipment, checking if there are any issues with existing products, to determine whether a product conforms to specifications and standards, to check that an assembly process has been completed successfully, and to test samples of products before they are sold to consumers. Acceptance sampling allows companies to determine if their products meet their standards before they begin mass production or distribution. If it does not meet their standards, they can reject that batch and start anew instead of continuing down the path towards producing something less than satisfactory quality-wise. This also reduces cost by eliminating the needs to test every unit and helps ensure that the quality level of your products meets expectations and standards, which means fewer returns and consumer or customer complaints. A sampling plan specifies the parameters of the sampling process and the acceptance or rejection criteria. There are different types of sampling plans. We have the simple sampling, the double sampling, and the multiple sampling. Let's have the first one, the single sampling. It refers to a sampling method in which a random sample is drawn from a lot. Every item of the sample is labeled as good or bad after inspection. The entire lot is accepted or rejected according to the quality of items. In single sampling, the maximum number of defects is defined based on which sample is selected. This type of plan is commonly used when inspecting products that are manufactured in small batches and are made using highly automated processes that makes it difficult to inspect each individual unit before assembly. So here are the procedures of the single sampling plan. First is collecting a random sample from the lot for inspection, inspecting the sample for the required quality characteristics, accepting the lot if the numbers of defects in the sample are equal to or less than the number set in the parameters, and reject the lot if the numbers of defects in the sample are more than the number set in the parameters. The next types of sampling plans is the double sampling. This involves sampling the lot if the results of the first sampling are inconclusive. This type of plan is commonly used when inspecting products that are manufactured in large batches but where there are no automated processes involved by producing them. So here are the procedures of the double sampling plan. First is collecting a random sample from a lot for inspection. Second, inspecting the sample for the required quality characteristics. The third one is accepting the lot if the numbers of defects in the sample are equal to or less than the number set in parameter, say C1. Fourth, reject the lot if the numbers of defects in the sample are more than the number set in the parameter, say R1. Fifth, selecting another sample if the total number of defects is more than C1 but less than R1. Sixth, accepting the lot if the total numbers of defects in both the samples are less than the acceptance number C2. And the last is rejecting the lot if the numbers of defects in both the samples are more than the rejection number R2. The last type of sampling plan is the multiple sampling. It involves sampling of more than two samples. It is extension of the double sampling plan. The process of drawing samples is continued till the decision of the acceptance or rejection is not taken. A multiple sampling plan involves smaller first samples than single or double sampling plans. It is comparatively difficult to design and explain and expensive to administer. It involves a higher overhead cost as compared to single and double sampling plans. It involves more record keeping. In theory, multiple sampling may often permit lower total inspection than double sampling for a given degree of protection because of the smaller sample sizes required. New methods which simply multiple sampling, such as automatic sampling boxes, may result in greatly improved efficiency in administering multiple sampling plans. Selecting the type of sampling plan is dependent on the cost of collecting a sample and testing it. If the cost is high, the single sampling is preferred. This slide shows operating characteristic curve. The operating characteristic curve reveals the capability of the sampling plan to discriminate between the good lots and the bad lots. The curve indicates that a lot with some defective percentage would be accepted based on the result of the sampling inspection. In the curve, the x-axis shows the percentage of the defectives, and the y-axis shows the probability of the acceptance of the entire lot. The OC curve is an S-shaped curve that implies that the probability of acceptance increases as the number of defects falls. There are four parameters of the OC curve or the operating characteristic curve. The first one is the producer's risk or the alpha. This refers to the probability that a good lot or non-defective would be rejected by the sampling plan. The risk of rejecting this lot is 0.01% to 10%. Sampling plans are often designed to have the producer's risk set at 5%. The next one is the consumer risk or letter B. This refers to the probability that the bad lot would be accepted that contains a greater number of defects. A common value for consumer risk in sampling plan is 10%. The third one is the acceptable quality level or the AQL. This refers to the maximum percentage of defects that consumers are willing to accept. AQL is considered satisfactory. And the last one is the lot tolerance percentage defective or the LTPD. This refers to the percentage of defects more than AQL, which is not accepted by consumers. This has a low probability of acceptance. So there is a video on how to create an OC curve, so let's watch.
So let's talk now about how to create an OC curve. So essentially what we do when we create this OC curve is we're calculating a probability of acceptance using various incoming quality levels, okay? And we do that using the binomial probability equation. And so there are four main parameters or variables here in this equation. The first is the acceptance number. So you actually won't see the variable C here, but what you do see is the number D. And so I want to explain the relationship between the acceptance number and the number of nonconformances observed. Now the sample size n does show up a number of times in this binomial probability equation. So you see it here, n factorial, n minus d, and then you see it here in this exponential. So that's the sample size. D is the number of nonconformances observed. And so when we go through our example, I'll show you how that number of nonconformances relates back to the acceptance number. But essentially, this is the outcome of your inspection. So you can't really define D, it's really just a result of the inspection that you perform. And then P is the x-axis here. It's a supposed or a hypothetical incoming quality level. And then for each of these incoming quality levels, we'll calculate the resulting probability of acceptance. So let's do an example. So let's say your sampling plan has you sampling 60 components, that's your sample size, and you believe that the overall percent nonconformance from this purchased vendor lot is 1%. That's your incoming quality level. You will accept this lot with one or fewer defects. So C here is your sampling number. This is the accept number. So you'll accept on 1 reject or 0 rejects. What is the probability that one or fewer nonconformances will be found in the sample of 60 when the incoming quality level is believed to be 1%? So let's talk about probability. So if you remember back to statistics, when we talk about probability, specifically when we have more than one outcome, we have to do what's called cumulative probability. So the probability of having one or fewer nonconformances is equal to the probability that you have 0 nonconformances plus the probability that you have 1 nonconformance. So there's 2 outcomes here that result in us accepting the lot. And we want to understand what the probability is of accepting the lot. So we have to understand the individual probability associated with each outcome. So in blue here, this is the outcome where we complete the inspection and we find 0 defects. And this here is the scenario where we complete the inspection and we only find 1 defect. Every other outcome, whether it's 2 defects or 3 defects or 4, all of those get rejected. So here we're trying to calculate the probability of acceptance, and that's these 2 outcomes. So here's that binomial probability equation. And so let's look at what this looks like for 0 defects. So the probability of performing this sampling plan on 60 units and finding 0 defects is essentially we can plug in all of our variables and calculate a 54.7% probability. We can perform that same binomial probability equation for an outcome of 1 defect. So you'll see how that changes. This becomes 1 factorial, this becomes 60 minus 1, which is 59 factorial. We have our P, our incoming quality level, raised to the 1, and then essentially we have this number raised to 59. So that changes the equation slightly, and the probability of performing the sampling plan and having only 1 defect is about 33.1%. So cumulatively, the probability of both these outcomes combined is about 87.8%. So let's see what that looks like graphically. So here's that problem statement, and here's our OC curve for this given sampling plan. So what we just calculated is this data point right here. So when our incoming quality level is 1%, the probability of acceptance is 87.7%. As our incoming quality level changes, the probability of acceptance falls. So essentially all we have to do is repeat this calculation at different levels of our incoming quality. These 3 things would stay the same, this variable would change, and then of course we just calculate these different probabilities of acceptance. So this is how we create the OC curve.
That video is the OC curve for a single sampling plan. So here are the examples of a double and multiple OC curves. Computations are the same in the single sampling plan. As you see in the picture, data encircled are used to plot to make a curve for the possible quality percentage of the product to be rejected or accepted. In most sampling plans, when a lot is rejected, the entire lot is inspected and all defective items replaced. Use of this replacement technique improves the average outgoing quality in terms of percent defective. In fact, given any sampling plan that replaces all defective items encountered and the true incoming percent defective for the lot, it is possible to determine the average outgoing quality or the AOQ in percentage defective. Here is the equation for AOQ. Acceptance sampling is useful for screening incoming lots. When the defective parts are replaced with good parts, acceptance sampling helps to increase the quality of the lots by reducing the outgoing percent defective. This figure is the application of statistical process techniques contributes to the identification and systematic reduction of process variability. This shows acceptance sampling by definition accepts some bad units. Control charge by trying to keep the process in control, but the C-index places the focus on improving the process. The operations managers, that is what they want to do is to improve the process. Here are my references. To end this report, acceptance sampling can be used for testing both the physical and functional properties of products. So it is used to measure quality control, as well as to test the quality of manufactured goods or materials. It can also be used for testing samples from customers. The process involves first determining the size of a product lot to be tested, then the number of the products to be sampled, and finally, the number of defects acceptable within the sample batch.